Thanks so much for the introduction and also for inviting me to speak today. It's very nice to be here in Hong Kong. I was just sharing with everybody over the dinner and the lunches that it's been 20 years since I've been to Hong Kong. I came here when I was a kid, actually, and it's really nice to see the changes that's been happening. So I'm going to take, this talk will be somewhat along the lines of experiences that I've had working with robots over the past few years. And what the purpose of my lab is really to develop AI for human-robot interaction. So I'm interested in robots that are effective, meaning that they can work with you to accomplish a goal. They are fluent, so you don't need a degree in robotics in order to work with a robot. And they're safe, so they shouldn't kill you or harm you as part of the process. Now, this is extremely challenging, and I'm interested in this because I'm interested in robots that can work with the elderly and helping them in their homes, which is very far off. So it's not the thing that we can accomplish maybe in 5 years, but I'm looking at it as a career-long goal. Now, what is a kind of approach that people are trying nowadays? I think perhaps this is what is attracting a lot of attention in that we have a model called a visual language action model. Quite simply, you put in some vision, you put in language, and it outputs actions, what the robot should do in a particular situation. Now, the question is, can this work, right? Is this plausible to do? Because what you would do is, if you had such a system, you would train it with data end to end, okay, to try to output appropriate actions. This is quite hard, I would argue. Why? For various reasons. But you can think of it as you're trying to generate a distribution, or you're trying to model a distribution of actions. And you can think of this as actions can be arbitrary, okay, but let's think about them in terms of grass poses just to ground it, okay? So I'm generating some grass poses. I'm not really interested in generating, just a distribution of actions. What I'm interested in is generating the probability of an action. I'm trying to model the probability of an action given a particular goal and context. So let's ground that a little bit more. I'm holding this mic here, right? I'm not interested in just any grass pose when I'm holding the mic. I'm interested in a grass pose that holds the mic in a stable fashion. So I need to hold it firmly such that it doesn't fall out. Okay, if you think about it, it's not just, and even if I'm a millimeter off, the mic will fall. I think Chachun gave this example yesterday as well, which I think is very illustrative of the problem that we're facing. So why is this challenge? Is because in order to generate appropriate actions, you need to have understanding of the world, both physically and if you're interacting with people, socially as well. We don't just arbitrarily take actions with people. There are established norms that we have to follow. One major issue that has been cropping up again and again is data scarcity. We don't really have action data. It's very, very hard to come by. So how do we train such a model end-to-end if we don't even have the supervised learning signal? This is very difficult. And finally, we want to be safe. So it means that parts of this action space will be no-go, right? We are not allowed to do it because we might harm a person as a result. So what's the key idea I want to basically discuss or get your insight on for the rest of today's talk will be about not making your model's life harder than it needs to be. Okay, what does that mean? So I think that there are two key ideas I want to get across is that I think we should leverage sensing more. And in the previous image that I showed you, the input was mainly vision and language. And one key notion that we have in robotics is that maybe you don't compute something that you can more easily sense. All right, we should leverage sensing in order to be essentially outsourcing our computation towards more established sensing mechanisms, okay? And the second was nicely illustrated in the earlier talk, actually, about leveraging structure and priors. If you don't have enough data, then the information has to come from somewhere. And one way you can put information is through putting some structure into the model or to establish some priors. And the priors can either be some expert knowledge or something that you extract from a foundation model that has been consumed by large amounts of data on the internet, and then you're extracting that somehow to put into your particular structure. Okay, so the work in my lab revolves around some of this, and I'll talk a little bit about that, but we want to do this AI for HRI thing. And I'm going to talk about leveraging sensing in terms of touch. All right, I think that touch is very interesting because it can reveal something that vision maybe cannot. So for example, as I'm holding this remote, right? You know I'm holding the remote, but you don't know how hard I'm touching the object because the forces are not visible to you, they're invisible. But tactile sensing can reveal these forces to you and reveal something about the action that I'm taking. So we've been doing some work in this area. I'll discuss a little bit about that. The other aspect I think is important is social understanding, and we'll be building models for understanding and modeling people. And this takes different kinds of forms. We started off very early looking at Gaussian process models, which are kind of old now, but then we've been leveraging foundation models, again, leveraging priors from these models that have consumed large amounts of internet scale data. So I won't talk so much about social intelligence today. We'll talk more about this aspect of machine learning for robotics. So a lot of the models that we've been building rely on machine learning, as many people here do. And we've been working on diffusion models. And yesterday, we saw some nice talks on diffusion models. We've been working on that as well. And I'll talk a little bit about that, how to constrain the models in order to obey instructions, so instruction following. Okay, I want to say that all the work that I'm going to present today is really thanks to my students. I like to say I'm just a marketing guy. I just come up here and tell you about the work, but really they're the ones doing all the hard work and staying up late and training the robots and breaking the robots and fixing them. It's a hard work when you're working with physical systems. So yeah, these are my amazing students, and also thanks to my grant agencies and my funders. So let's start off with physical intelligence via touch perception. So when I was a PhD student, there are many PhD students here, I think. So if you're a PhD student, are you PhD students? You can raise your hand so I know who you are. So I think that part of this, thanks to Yima's keynote opening statements yesterday, I think part of the talk is about basic questions more than answers. So I'm going to ask a lot of questions, I think. And when I was a PhD student, one question I had was, okay, whether we could really understand worlds through physical interaction and interpreting these tactile sensors that are coming back in. So we're playing around with iCup robot. This is quite old now. This is like 2012, I think. It couldn't even walk. Nowadays, you have robots that walk around like this robot couldn't walk. But it had these very nice tactile sensors on its fingers, capacitive tactile sensors. And what we were trying to do is to recognize these objects by touch. And we were doing it in an online fashion. And we built this kind of generative models. This was a generative model circa the 2010s. This is quite old now. But essentially, what you would do is you would build these experts that try to predict the tactile signals that you would observe or potentially observe given particular interactions. And then based on the actual real observations you get, you can apply a Bayes filter and then make a prediction about which expert was correct. And if each expert was an object class, then you would know what object you were interacting with. Okay, and this was a simple application of Bayes rule, which we talked about earlier. So I grew up as a Bayesian in my PhD. Okay, so since then, I took a hiatus from tactile learning for a long while because I did a postdoc and it had nothing to do with tactile sensors, so I didn't do that. But when I started my faculty position, I started this program up in tactile learning again. So one of the first projects we started off was to look at how we can combine vision and tactile together. And we were looking at these event-based sensors. So I'm sure many of you, if you play with vision, you have these event-based vision sensors. We were trying to use event-based tactile sensors in addition to event-based vision sensors. And the takeaway there was that we can really combine these two to get very low-powered, efficient tactile perception. Then we moved over to looking at interaction through tools. So I don't know about this about your human beings have this amazing perception ability when it comes to touch. So if I'm holding this object, I can interact with other objects. So for example, I can touch something and I know I can infer the point of contact, but not only the point of contact, but the type of object I'm interacting with, whether it's hard or soft. What this means is that it's as if you have virtual tactile sensors on the object. We can extend our sense of perception through rigid tools. And that enables us to use things like screwdrivers and hammers because we can feel through objects. And what we show is that robots can also do this if you have the right machine learning combined with the right kind of sensing. What is important is that you have high enough frequency to detect the vibrations, because how this works is that the vibrations travel up the tool, is picked up by the mechanoreceptors in my skin, is transmitted through my nervous system to my brain, which then interprets the signals. So that's how it works in a human body. And then we replicated this to some extent in a robot. And making sure we can recognize different types of food simply by using a regular fork, right? That you can buy from IKEA. And then more recently, we've been trying to build more or less foundation models for touch. And this is the part that I'll talk about in today's talk. So we're not the only ones. This work came out in RSS in 24, a year ago. We started it in 23. But there were other works that came out approximately at a similar time, looking at the similar sort of idea. So I think it was this idea that was ripe right? It was the right kind of ingredients were all there, so it was just putting it together. And that's what my student Samson and Kelvin, my RA Kelvin did. So what's the idea behind this? So when we were building tactile models in the past, how we would do it is, if you have a particular task, let's say you were trying to classify how ripe fruits are, you would gather a bunch of data for how ripeness felt on the tactile sensor, okay, which is shown by that image over there, or video over there. And then you would build a fruit ripeness model. And this fruit ripeness model is a classifier, essentially. And if you have a different task, let's say classifying objects, you would collect data, and then you would do it again, okay? And then you classify the object. But there's some noise, but okay, never mind. But what you can do instead is to build one model, right? For all these different tasks, and instead of switching between models, what you can do is you just change the task prompt, which is like, what you would do with ChatGPT, for example. Okay, you change the task prompt, and then the model would then output the right output given the context. So if in the case was avocado, it would detect whether it was ripe or not. And this one, if you're detecting what object it is, then it would try to classify the type of object. This is nice because what it allows us to do is enables to leverage common sense reasoning. I was talking about priors before. And these models have consumed large amounts of data, so it knows things like soft objects or soft fruits tend to be ripe. So we can leverage that because that has been, it has been consumed by the model, already been learned by the large language models. What it also allows us to do is to enable physical grounding for LLMs. So LLMs don't know what it means for an object to be soft or hard. It doesn't have that kind of grounding. But by training models in order to recognize touch, then we can enable this kind of grounding for the LLMs. The big challenge, of course, is domain gap. There's not enough data, again, back to the original point. So we needed to collect a data set. This is the example data set. We have about 123 items. It's not very big, okay, but it's big enough for this kind of data. This data is very hard to come by. It's painful to collect. You can see the different kinds of tactile signals that you can get here from a gel site sensor. This is a sensor that you can buy off the shelf. Costs about 500 Singapore dollars, about there. It is a high resolution sensor or optical based sensor. So you can imagine a gel pad on top that deforms when you come in contact with objects. And there's a camera essentially that detects the deformations. And then this gives you some signals, okay? Now, I'll show you a picture of Kelvin. This is Kelvin, who is collecting data. This shows you the data collection process where he's taking it, twisting it, and touching it in order to generate the data. Now, this type of data collection can be quite painful because the sensor itself can be quite fragile, right? So we've torn many sensors as a result of this process, which again is one of those things that you should be aware of if you want to do this kind of work. So when our previous model essentially was Octopi 1. This was our first attempt to build a large model for this. We used a Vicuna 1.5 model, and a lot of the effort actually was into this encoder, right? We spent a lot of time trying to train this encoder using the data we have. This was consuming lots of GPU hours, as well as hand tuning in order to get it to work well. So once you train such a model, you can do things like this. Please pick the ripe avocado, and so it's going to touch the two different avocados on the table, because from vision, you can't really tell which one is the ripe one. But after you've touched it a little bit, then Octopi will start to reason about, I'm using reasoning very loosely here, but it's going to use reason in order to figure out which one was softer. Okay, it describes the tactile sensations that it gets, and then it does this verbose, like chain of thought thing that tries to figure out, okay, which one is softer, and then it picks the right one. Okay, so this was in RSS 24. This year, we had an updated version, which is 1.5. So we upgraded the LLM to Q1, which is a better model. And then we replaced the vision encoder. So what we did with Octopi 1 was to co-opt the vision encoder. So we took the vision encoder, and then we made it into a tactile encoder. But this then meant that the model could no longer process regular vision images. But now we've replaced the vision encoder. So now we can process both vision language, as well as tactile encodings. And we updated that with more data. And also we added the retrieval module. So what the retrieval module would do is that whenever it encounters a particular object, it would look into its database of tactile sensations that it's seen before, objects that it's seen before, basically its training data set, and then they can pull out relevant information that it's seen in order to enable it to make better classifications. And we see this in the data as well. So this is a demo of some of the things you can do. You can take a picture of the scene. In this case, it uses the camera there. Okay, can we mute the sound? Sorry, can we mute the sound? Oh, you cannot mute the sound? Okay, sorry about that. I forgot to mute the audio. But okay, so what you see is that what Octopi is doing is classifying is telling you the object property. So it says the object 4, what is grasp, is firm, smooth, slightly waxy, and hard. And it's pulling out other objects from the training data set. So it already says that, okay, the most similar objects that it's seen before are, a ripe apple, wooden ruler, and so on and so forth. And then based on what the picture is, it tells you to detect what it is that is touched, okay? Okay, so as I mentioned before, what we see is that improved performance by using a larger model as well as the RAG. So when you were using Octopi 1, you get about 40% accuracy. With Octopi 1.5, with no RAG, then you get a little bit beyond 50%. But with RAG, you get significantly better performance because you can be able to retrieve the relevant amount of information from the things that they've seen before. Okay, so that was about language. So we were able to then connect language to touch, which gives us this interesting modality. Now, how about we getting to actions? Remember, I want to say we want to generate actions. So in the previous model, you had instruction coming in, you had vision, and then it would output what we call an action chunk. You can think of it as a small sequence of actions that the model needs to perform or the robot needs to perform. So now I have tactile information. How do I start to modify this VLA? Now, there are very many designs that you can take. What my student Jensen did was to try to take the simplest design, so with minimal training, because we don't have that many GPUs. So what we did was we tried to keep the modules as the same, okay, but try to modify them in the smallest possible way. So let's try to do that. So what he did was to try to refine actions using touch. And the key idea here was to leverage an interpolation-based model. This interpolation-based model was something that we published in RSS. Essentially, you can think of as flow matching, but an SDE rather than an ODE. All right. I think Signing yesterday presented some stochastic interpolant transformer. I think came out about the same time. This was applied to policies. Okay, so you can generate robot policies this time. Compared to diffusion, if you know diffusion, you usually start from a Gaussian, and then you map that to a particular distribution that you're interested in, your target distribution. Here you can start from arbitrary distributions, as long as they have the same support, and move your way to any target distribution. What this allows you to do then is to leverage prior knowledge. So you can start from a distribution, for example, of robot policies that exist, handcrafted robot policies, for example, and then you can move yourself towards your target distribution using data. Okay, so you have your bridger model. This allows us to take into account our tactile inputs, so we don't have to feed them necessarily direct to the VLA, but we can put them only into marker tracking, which is the handcrafted solution that Jensen came up with. And then we can also use Octopi in order to have a task planner on top of that so that we can do both low-level control as well as high-level planning using tactile information. So what can you do with something like that? Let me show you an example. So this is a robot which is asked to clean the plate using the smoother sponge because I don't want to scratch my plate. So here the robot is going to touch both sponges. It touches the first one and it says, oh, this is too rough. So I'm going to touch the other sponge. And they say, oh, okay, this one's fine. So then the VLM will say, okay, now you can use it to clean the plate. It grabs the plate and then it starts to clean the plate using this object, using the learned policy. Okay, so that's what it's doing. And there it's using its tactile input in order to control the sponge appropriately. This is a more challenging task where we are doing peeling. So here the robot is asked to pick the right mango and then peel it. So it uses the VLM to pick the right mango, but after that, it tries to peel it. And then this is again using its sense of touch in order to control the peeler appropriately so you don't accidentally damage your mango. Okay. Okay, so using this kind of approach, what we see is that we are able to get better performance the moment we start incorporating tactile information. All right, that's just a takeaway. You can look at the graphs later if you want in the paper. I would like to say, however, that we are still far from an ideal architecture. We are just taking steps in one direction, right? This is the simplest possible design that we could come up with in a really low compute setting. However, if you have more compute, then you can try different kinds of designs in order to improve upon this. So the key idea behind all this work is really that we can leverage tactile inputs to improve task performance. And I think that it can reveal something about actions, which is what makes it so effective in actual real-world robotics. You can leverage, again, prior knowledge, and the prior knowledge that we're leveraging here is both in terms of the model design, but also in terms of the prior information that's been put into these large language models. So common sense reasoning, common sense knowledge, as we usually say. Finally, as I mentioned before, the design space is wide open here. There are many ways that you can construct such a model, and that's what makes this feel so exciting, I think. There are many possible designs with different explorations of the Pareto frontier, okay? And I think that we are not anywhere close to finding out what is the right design yet. Okay, so that's on the physical intelligence via touch perception side. I think I have a little bit of time, so maybe I'll ask I'll stop a little bit here for questions. Does anybody have questions regarding the work? Okay, if there are no questions, then I'll move on first. I'll move over to this side. And I'll talk a little bit about how we can constrain models or constrain these generative models to output what we want. So I think that yesterday there was from Junsu, he was talking about diffusion models, and there were many talks on diffusion models. And people have been using diffusion models also for policy learning. There was work out of MIT, and then also from Shiran Song's group, that time in Columbia, and now at Stanford. So why might you be interested in diffusion as a policy class? Sorry, give me a second. Move too fast. Okay, so it's an expressive model class, meaning that you can model essentially multimodal distributions. And multimodal means multimodal in the distribution of the action space. So here, for example, diffusion policy, you can model these two different ways of going from the blue dot to pushing the T. Okay, this is the push T task. I think it's fairly famous, but the idea is that you want to push that gray T to match the green marker. Okay, so that's the objective of this task. And if you use something like STM-GMM, you see that it tends to favor one mode over the other. Okay, so this is why you might be interested in the diffusion models. And you can represent high-dimensional continuous states and actions, which is really useful for robotics. Okay, so people have been using these diffusions models, so you can do things like, I want to push this T block into the right shape. My question is, what happens when you start having some safety or norms? So you notice these circles here. What happens if I say, like, don't touch P1 and P3? Well, if you're using the original policy, then it doesn't do that. Okay, it will violate these constraints because there's no way of incorporating that directly into these diffusion policies at first. But if you do things a little bit differently, and I'll talk about how you do this, you're going to be able to avoid the P1 and P3 dots there. So you see the circle, the way your robot moves, it avoids these areas that you don't want it to touch. And you can do things like, hand over the hammer. This, again, it will leverage some amount of common sense. So, for example, if I'm handing something to somebody, I don't hand it over by, I hand it so that they can grab it easily from the person. So if I hand over a knife, for example, I don't do it with a knife edge pointing towards you. That's considered rude and also unsafe. So I'm going to talk about two different ways you can do it. Okay, the first way is using logic and classifier guidance, and the second way is using key points and constraint embedding. These are just two different approaches. You can pick which one you want to use depending on your particular task context. Okay, so let's start with logic and classifier guidance. So here's the problem setup. I have a particular diffusion model, all right, P theta, and it generates a path, let's say like the one shown here. And now I would like to constrain it in some way. So I have a particular constraint, okay, an evaluator. So I must be able to evaluate whether the constraints have been satisfied or not. This is a requirement for my setup. And what I would like to do is to generate actions that satisfies this constraint. All right, this is what I want to do. And so the method here is called LTR-dog. You can read more details in the paper, but I'll give you the overall highlights, okay, of what the key technical results are. So quick skinny on diffusion models. So we've covered diffusion models before, but just to keep everyone up to date, if you weren't here tomorrow, how the diffusion models work is that you want to generate this target distribution here, PA naught, and you generate it via a distribution Gaussian. You sample action from Gaussian, a unit Gaussian, and then you gradually transform it into the target. Okay. Now it turns out it can be quite hard to learn this distribution. So what we do is that we construct a variational distribution Q. Then this variational distribution Q is constructed very easily. We take that clean signal, we gradually add noise. Okay, and eventually you add noise enough, you will arrive at this 0-1 normal Gaussian. Okay, and now what this allows you to do is that it gives you the marginals that you can follow. You can learn to map in the opposite direction. Okay, so that's a key intuitive understanding of how these diffusion models are trained. So after you train the model, what you obtain is this score function, right? And people were talking about the score function yesterday. This is the key element that you try to learn as part of this reverse process in order to generate a clean signal from a Gaussian. So what's the high-level idea behind Little Dog? It's very simple. In each of these diffusion steps, okay, you would try to clean up this trajectory. And what we want to do is to incorporate some guidance from the constraint. All right, so if my constraint is never enter the red regions, then I have this differentiable constraint checker, which provides me gradients that I can then use to modify my action as I go along. Okay, so that's a very simple idea of what we are doing. There are two questions that emerge, is that first, how do you specify these constraints? Okay, and the second is how do you combine this checker with diffusion? So let's start off with how to specify constraints. We are using something called LTL, okay? So LTL is linear temporal logic, is a kind of logical specification. Why would you want to be interested in using LTL? It's because it's a very flexible language for specifying both static and temporal constraints. So you can say things like don't enter the red squares, but not only that, but you can say don't enter the red squares until you enter a blue square. That means after you enter a blue square, you enter the red square. So you can specify these things in very flexible way. Not only that, but it allows you to also check appropriately. All right, so this is a model checker. So you have guarantees essentially that whether this is a correct action to take or not. So this ties back to the notion of safety that I was talking about before. And this phi here is this LTL formula that I want to obey. All right, I want the robot to obey. I'll skip over the specific form, but essentially you can transform natural language into these logical descriptions that then you can plug it into your model. All right, so I can do things like never touch P1 and P3, and then you want to visit the kitchen before the passageway, and that's how you specify it within the context of LTL. Okay, so I'm done. I know how to specify my constraints and how to check them because I have a small checker. How do I combine this checker with diffusion? So if you know classifier guidance, you know this particular form. What you have is you can decompose this diffusion process into two parts. The first part is on the left, which is your standard score, which I talked about earlier. On the right-hand side, this is the classifier guidance, okay, the gradients from your checker, essentially. And we need that, okay? So what we used this tool, which is a differentiable soft constraint checker, which came out in Europe a couple of years before our work. But you have to be a little bit careful here. So when we first tried to do this, it didn't work, okay? And the question is why didn't it work, right? It seemed quite straightforward that you can just use such a checker and then modify the constraints. You have to be careful about the interpretation of this particular term on the right-hand side, okay? This doesn't say that AT, when you're doing your diffusion process, you're diffusing these actions, okay? It doesn't say does the diffusion at point T, at step T, does this satisfy the constraint or not? That's not what it's checking. It's checking whether if you follow this trajectory along, if you reach the target, the end terminal, A naught, does the expectation is this constraint satisfied? Okay, so you have to be a little bit careful about the interpretation. So when you do this, then the way to fix it is to do something like posterior sampling. This is an approximation, it's very simple. What you would do is you predict the expectation of A naught given AT, and then you plug it into your differential model checker. So this you can think of as a first order approximation to establishing whether your constraint is satisfied or not. And in practice, it works well enough. If you cannot differentiate through, there are certain circumstances where this can happen, then you need to learn a kind of a guidance, okay? And then you can learn this as well in a standard approach, okay? I'll skip the details. But here we have a GNN, okay? In order to learn these constraints, and then we can plug this directly into that form over there, all right? Okay, so we've answered our two questions. Once you've answered these two things, you can start playing around with this model. So you can start to get the model to obey constraints. So the baseline here is a safe diffuser. What we want to do is to get this model to avoid the red squares. What you notice safe diffuser does is that it cheats a little bit because it's a local model. So it teleports the robot across the square, which is not valid, right? You can't get your robot to teleport. If I could get my robot to teleport, it would satisfy a lot, it would solve a lot of problems, but I can't do that. What LTL dog allows you, or Little Dog allows to do, is allow you to find alternate paths in order to find the solution. So here are just some numbers, but essentially the numbers just show you something simple, that you can have high satisfaction while not sacrificing too much reward, okay? And reward here is the number of steps you take to arrive at a particular goal location. This is some videos for Pushti. I showed this before already. This is just showing you that the model that we created was indeed used to generate the videos of avoiding the particular zones, okay? So these are some real robot experiments for navigation, where we are trying to get the robot to obey certain constraints. Again, we use something like the natural language utterance. We convert it to logic using ChatGPT so that you don't have to know how to write the logic yourself, but you can check it. And then we tried this in different environments. Here's just a couple of videos. They're very straightforward. Essentially, on the left is the baseline model. This is the model that we've trained. And what we would like to do is hit the green spot, but avoid the red spot. And if you look at the videos, what you see is that the robot obeys the constraints that we set up, okay, for this particular problem. Here, we want to visit the regions before we get to a target location. If you just use the standard model, it'll just take the shortest path. But because we want it to obey the constraints, it takes a longer path, but it obeys what we want. Okay, and then there's different settings for this particular task. So you can have your robot walk around, yet obey the constraints that you're interested in. And here, you're going to avoid the red region, which is this thing over here. So the diffusion doesn't work. This one takes a slightly wider detour in order to avoid the region. Okay, so I'm going to skip that video. So what we have at the end of the day is that the key idea is really that you can guide the diffusion process using a model-based method. So here we've leveraged prior knowledge. The prior knowledge is encoded in the model checker, all right? And it gives us some guarantees about what we want the robot to do. And yet we are still able to use this rich data-driven policy class in particular diffusion models, but get it then to obey constraints. And then we have these guarantees along with it. There's some additional new work that just came out where we've tried to close the loop. There we've done, 5 minutes left, okay. So here we try to make it hierarchical and also close the loop, and you can check that out by following the QR code there. Okay, so I'll quickly go over the last piece of work, which is about Disco, and this is my student Che. Here the setup is a little bit different. What we're going to do is in painting, and the idea is very simple, okay, and people have already explored similar things in the literature. So we would like to have some open vocabulary task instruction, and I assume that I have some multi-view images. And what ChatGPT is going to do, I'm going to ask ChatGPT to do is provide some keyframes that allows me to obey this constraint or the instructions that I give it. And so ChatGPT is going to output the keyframe, okay? And then I want the model to obey, okay? I want it to generate actions, or in this case, thrust poses and trajectories that obey this constraint. So the technique we're going to apply is called in-painting. I think many of you may know in-painting because if you play around with diffusion models, you know in-painting. You have particular base image. I can have some mask, and then I can generate image, in this case, a cat here that replaced that mountain that I've masked out, okay? We can do the same thing with policies, all right? So if you have a particular trajectory that you want to generate, then what you can do is that you would have particular executed actions here. You have a history, okay? And I will provide a keyframe condition. So forget this side, just look here for the intuition. I have a history. My keyframe comes from ChatGPT or something similar, and I'm going to generate some samples to connect the two together. Okay, that's the idea. So now, what is the problem? The problem is that what you discovered is that the keyframes coming out of ChatGPT can be quite lousy at times because these models sometimes don't have a good grasp of spatial world. As we discussed earlier, their spatial understanding is not very good. So if I say hand over the hammer, sometimes it will give me something good, like keyframe A, this is good. Keyframe B is bad, okay? So because it will try to pass through that point, which is not accurate. So how do I constrain the model further in order to deal with this particular problem? And the key idea is very simple. At a high level, what we're doing is constraint in baiting. So keyframe A is in distribution, so it's good. Okay, keyframe B is out of distribution. I don't like it because once the model goes out of distribution, it tries to match the keyframe, but it will go out of distribution. Once you go out of distribution, the diffusion policy craps out. Okay, so we don't like that. So what we do is very simple. We establish a simple constraint threshold, and then we just optimize an action within that constraint threshold. Okay. And then once you do that, you see significant performance compared to the others. I'll skip over the performance results. You can see them in the papers. But as usual, the performance result just shows, oh, we're better than others. Okay, nothing new. And then here are the more instructive videos where you can see, okay, the robot starts to obey certain things. You can use the common sense region, the common sense understanding from the ChatGPT model in order to output valid keyframes. But you can constrain the model so that it uses the keyframes appropriately. This is examples of grabbing the handle and grabbing the top. Okay, and then these are the videos. I'm going to skip that. Okay, so the key idea here was very simple. We have the rich data-driven policy class, again, just using a diffusion model, but now combining with a VLM in order to get out keyframes that we can get the model to obey. And then we can get robust performance, provided you use this constraint optimization technique. Okay. So this is the end of the kind of technical content. I think I'm within time. I'd just like to mention a little bit about challenges ahead. So I think that one of the biggest challenges we're facing right now, when I talked about multi-sensory, so I want to leverage multiple sensors. But the problem is that data for these multiple sensors is hard to come by. So we've tried to provide some of the data for tactile inputs, but there's a lot of kinds of inputs you can imagine giving to your robot. So for example, you could smell. Okay, you can have more audio, and people are exploring audio. There was a whole bunch of audio papers at Coral and RSS this year. And then beyond sensory, there's also about alignment. I talked about alignment to more explicit constraints, but how about implicit constraints? How do you put all of them, these kind of different costs together in the same structure that enable guidance to occur in a simple, effective, flexible way? Right now, when we try to incorporate multiple guidance signals, you tend to find that your models actually don't perform well. All right, they tend to quickly go out of distribution, or it fails at a particular point, partially due to local minima in the energy surface. The last important thing I think we need to push forward is long horizon tasks. So this is some work that Che just presented at Coral. And essentially there we're trying to get to many, many steps, okay, in the process. And one big problem we see is that, these large models, they have a non-trivial failure rate. So the moment you have a failure rate, then the failure for the whole task, the success for the whole task drops exponentially, okay? It decays exponentially, which is not great. So we need some form of error recovery, and this is even detecting errors is a challenge right now. How do you detect when an error has occurred, and how do you recover from it? We need to be able to do reasoning when you're going out of distribution. So when you're within distribution, then you can leverage on memory, because that's what memory is for. You can, you leverage what you've seen in your training data set. But once you go out of distribution is where reasoning really comes into play. So how do we encode these kind of reasoning modules into our large VLAs? This is not clear. All right. And finally, we need some sort of flexible, updatable memory. What does that mean by this? Your model, your VLA, essentially is memory. You are storing your data distribution into the weights to some degree, and then I believe you are interpolating between them rather than extrapolating. When I talk about flexible, updatable memory, it's things that after you deploy, things that you see and you have learned. How do you then update some external source that you go on the way? So I think that this is not quite clear how to do. We have RAG, we showed a version of this, but it's really primitive. So I think that there are much better ways to do this. Okay, so I'm going to stop here, and since I'm out of time, and these are some of the challenges that maybe you want to think about if you're trying to address problems in embodied AI. Thank you.
Thank you, Professor Harold. Any questions? Yes.
I have two questions. First, there was hello? Yeah, okay, just use this, thanks. So first part of your talk, you talk about VLA, vision language action, but towards the second part, you are talking about starting like a VLN, navigation. So as far as now, I might be wrong, the state of our VLA and the state of VLN, they're still studied in isolation. So what do you think prevents the community from building a unified model for both VLA and VLN?
That's a great question. So I think that, let me take a step back and then view things from a historical context for everyone here. So in traditionally classical robotics, we tend to distinguish between different kinds of tasks, okay? So the task space can be thought of as manipulation. I'm trying to move an object from point to point B. Navigation, I'm trying to move myself from point A to point B. And interaction, I'm interacting with an agent, okay? These are the three tasks. And the question you're asking is, we see some work on manipulation, we send some work on navigation. What about in the middle, right? And there is work in the middle. It's called mobile manipulation within the context of embodied AI. And people are trying to build VLMs and VLAs for this particular kind of task. It is more challenging for various reasons. So let me just give an example. Whole body motion is a problem. So to open a door, it's not as simple as I just reach my hand and I open the door. I need to open the door like this. So it's a combination of action that comprises my whole body. This is not so easy to control. This is it can be done in classical robotics. To learn a model to do that seems quite challenging at this point in time. We also don't have enough data for this. This is the second problem. So we've been looking at I agree, simulation is very important for this kind of things. sometimes it's not enough. So for example, the physical manipulation, particularly with soft articulate objects, is still very challenging. Getting enough data to train such a model in the real world is also very challenging, but people are trying to take steps in that direction. Most of it right now, to my understanding, are in simulation rather in real world, however.
I see. Good. My second question is a little bit more technical about the diffusion part.
Sure.
So I'm wondering, are you trying to do diffusion to decide the entire path, or you're doing this autoregressive plus diffusion like Kai-Ming's MAR?
Yeah, so there are two forms of diffusion that are used in policy, in robotics, I would say. So the first is what you mentioned, planning. Planning, you diffuse the entire trajectory, like the path through the maze, and there's diffusion policies, which outputs an action chunk. So you also a short chunk, and then you repeat this process as you proceed on. Okay, we use both. So the first work that I showed with LTL doc, this was planning.
Okay.
The second work was diffusion policies. So we output short action chunks as we go towards the target.
I see. Okay. Just like you mentioned, I think most of the work actually has limitation in long horizon kind of thing. A lot of things appear on very short memory.
That's right.
It's current images or just immediate previous images, things like that. Right?
That's correct. So to attack long horizon tasks, I think that the key idea is again it's not a new idea, it's an old idea. What do we do? We leverage structure, leverage hierarchy, right? So in order for me to get from here to the airport, I don't think about the entire short horizon path to the airport. I think about, I go to the hotel, I take a cab, or I go to the Hong Kong station, I take the airport express. I think at this high level goals, sub goals, and then I plan out the short-term trajectories to get there. So I think leveraging hierarchy is probably the way we need to go for these kind of
I
tasks.
see. Okay. Thank you so much.
Yeah.
Anyway, I think there's a long way to go. I mean, in terms of, leave the others things at the planning or decision making for control folks, but the sensing is important. You mentioned touch, right? So what's the status? I mean, what do you use? What's I worked at Berkeley with Meta for finger touch. Either very expensive or what do you think? I mean, you use some of the touch sensors. What's the tactile or whatever? What is your assessment of the state of art or the challenges?
Okay, great. So that's a great question. Tactile sensors are like, I would say, nascent at the point in time. It's not like cameras. The standards are not well established. Okay, so it's still very early days, I would say. There are many different kinds of tactile sensors. People always ask me, what is the best tactile sensor I can buy? My answer is always, it depends on your task. Different sensors will have different properties. So for example, the piezoresistive sensors that we use, they're very low spatial resolution, but very high temporal resolution. So the way you would detect textures is not like the gel sight. The gel sight has very high spatial resolution, very low temporal resolution. So with the gel sight with the camera, you can just imagine I just need to touch and I can see the texture. For a piezoresistive, what you need to do is slide. Once I slide, I can sense the vibrations, and then from the vibrations, I do this inference to figure out what the texture is. So it's less direct.
Like a visual based, right?
Yes. So the gel sight that I mentioned is this high spatial resolution, low temporal resolution. So it depends on your task, whether you're trying to recognize textures or to detect slip, right? Slip for robotics, I would argue, is a bit more important at a low level compared to texture recognition, but texture recognition may be more important at the high level task planning. So depending on what you want to do, then you will pick the right tactile sensor for it. What we're trying to do in the lab now, which is unpublished, actually halfway done, is to try to learn a model that can incorporate both. Right now, you see a lot of models, they either use one or the other, optical-based or piezoresistive or other kinds of sensors. I think that tactile sensors also is connected very much to actuation. So these two cannot exist, I think, separately. If you want to use tactile sensing effectively for dexterous manipulation, then they should be integrated into a hand or some form of actuator, okay, for it to be useful. This part, I'll leave it to the hardware guys to figure out, and they are producing better ones as we go.
Shape, but also it's the tactile is not just, it's actually multiple dimension, right? It's not just the shape, but also the force, right?
Yes.
Especially for safety, you need to apply compliances and so on.
That's right.
Haptic. In terms of sensing side, I think there's a long way to go, especially when you're doing manipulations, right? Grasping. Right now with simple grasping with a simple object is fine, hard object is fine.
Right.
But once with more, delicate manipulations and tactile, haptic, that's where the actuation and also sensing should go together. Right?
That's correct.
We apply a proper amount of force precisely because we feel very accurately the shape and also the force feedback. Right. Good.
That's right. So we have some work not shown here was we are manipulating tofu, which is very fragile, as you know. So we're moving tofu in order to feed people. We did a demo once to some government representative that came to see what has our funding bought us. So we have shown some work on delicate object manipulation in this space.
Sure. Yeah, please.
Yeah, so my question is, how do you feel like there's a solution to fuse the multi-sensory perception as you mentioned? Because we've got, I'm a mobile computing research student, so we have multiple sensor data, for example, like audio, acoustics, and also radar point cloud. So do you have any potential solutions to fuse all of these modalities into your VRM or something like that? Yeah, thank you.
Yeah, so this is a, I think, billion-dollar question, right? So people are trying to do this for VLMs, and large companies are trying to do this as well. I think that we don't have enough data to cover all possible combinations of this. So again, we should leverage some amount of structure. Again, this needs to be feedback, I think, to the way we learn the representations for it. And there's some work looking at how we can learn multimodal representations from an information theory perspective, trying to look at the redundancy between the signals, what is overlapping, what is not overlapping, and then trying to distinguish between them so that you learn the right information from the right kind of sensors. So for example, as I discussed earlier, tactile sensor reveals something about the forces that vision need not necessarily reveal, but there's also overlapping information about it. So vision can tell you already some properties of the object that I'm grasping. Jachin was sharing some of this yesterday. Tactile can reveal some redundant information about that. So coming up with algorithms and methods that can fully leverage this, I think, is important to develop. It's not just going to be, let's throw data in and hope something comes about. Just because of data scarcity, we don't have enough to learn all the correlations that we need to learn.
Hi, Professor. Thank you for your talk. And I want to ask one question that you mentioned that tactile sensing is really work really well with the sensing what the object is and doing some task. For example, you give an example that you are holding the black thing. I don't know what is it.
Remote.
Oh, right. You are holding this and you are asking. We don't know how many force you have applied to this object, but for a robot, it can get the force from its joint joint efforts or something else. Although it's not really accurate, but it's still one method to get how many force it will get from the collision or apply to the object. What do you think? This kind of the force control compared to the tactile, which one is better for the dexterous manipulation or some hard manipulation tasks?
Yeah, so that's a great question. It's about where your information is going to come from, I think. That's the heart of your question, right? Is it coming from a force torque sensor? Is it coming from a tactile sensor? Which might be better? Again, in robotics, usually my answer is very unsatisfying. It depends on your task at hand. So for example, your tactile sensor can tell you little things about if you're using a gel site, the texture properties, which you cannot get from a force torque sensor, right? And if texture properties are important for your task, so for example, one of my friends is looking at textile recognition. This is for particular industrial application. For that, a force torque sensor is not going to be so useful. So in that particular case, a tactile sensor is the right modality to use. I'm less concerned with, I would say, the exact form. I'm not a big proponent of one form or the other. I think really boils down to what's going to help the robot to complete its task. And it's very task-centric in nature. So yeah, I think that it's really about the information and how you process the information, the algorithms that you use in order to extract out the right signals to get the actions. That's what's the interesting part for me.
Yeah, I think it's also the problem for the multimodality data set, right?
Right.
Maybe some of the problem is that we cannot collecting both the tactile data set and the force feedback data set, right?
Yeah, so there are some attempts to do something like that already. And we actually, when we collect our data on robots, we do incorporate the force torque sensor data coming from the Franca Amica pointer robot. But that's a separate data set from what I've talked about today.
Oh, thank you.
Yeah.
All right, yeah, go ahead.
Hello, Professor. Thank you for your talk. So for robot-human interaction, we care about the users' modeling and we care about their users' intentions. For language models, I think they have some basic ability of theory of mind. So for example, for the hammer, if we give this hammer to user, we can infer directly the user might grab this side and they don't want to grab another side. So can we directly use this theory of mind instead of set different constraints to do these things?
Right. So the question is about theory of mind and whether large language models have a good enough theory of mind in order to use within an embodied AI setting. I think it has a first order approximation to a theory of mind. So we have some early work from 2-3 years ago, showing that you can extract out human policies from a large language model and then use that with planning. Okay, so you plan against a human model essentially, and you can get out good actions as a result. Whether it can do multi-turn theory of mind reasoning is still an open question. In fact, I think that recent work has shown that it can't really do that yet. So I think that I'll leave it to the large language people to try to learn such a thing. We have tried to do something in a different way. We were learning it using VAEs. We were talking about VAEs. We were looking at these sequential VAEs in order to learn latent spaces, and the latent spaces correspond to the person's beliefs or the intention at that point in time, and then using that for planning, right? So there's a different way of incorporating that kind of modality into your planning process. But yeah, it's still an open question as to whether it's good enough for everyday tasks. My guess is not really, especially for long horizon sequential tasks. It becomes very challenging.
Okay, thank you. I still have a second question. So for VLA models, now we have some method to generate data, then use the synthetic data to further improve it. So, but for the tactile data, I think it's hard to imagine how to generate it.
Yeah.
So do you think is there any method to do this?
Yeah, so I don't work on tactile simulation itself. There are many other researchers like Wen-Chen in Illinois who works on this. She does amazing work in that regard. To my knowledge, it's still limited to very much rigid objects and so simpler objects in order to generate tactile data. So we're far off from generating very realistic tactile inputs as, for example, for images. Okay, so we're very far from that. This is the problem that we are facing now in order to train models in order to use tactile information. Nevertheless, I have a belief that the tactile information maybe lies on even lower manifold than images. So maybe it's potential that we can learn this, even though the data looks very high dimensional, or at least the ambient dimensionality looks large. I think the real intrinsic dimensionality is actually relatively low. So if we can learn it, then I think it's useful enough for robot manipulation, at least for some tasks like SIP detection, things like that. Okay, but
Okay,
yeah.
thank you.